Okay, so now let's look at vectors and how we use vectors to describe motion. And so vectors are very important in physics because there's many quantities that we need to express mathematically, and the only way to do that is by using vectors. For instance, we've seen that speed tells you how fast you go, but velocity tells you how fast you go and which direction you're going. So those are two different quantities. You need a number to talk about the speed, but you need a vector to talk about velocity. Velocity is a vector quantity, a physical quantity that is described by a single number, like speed, temperature, pressure. Those are called scalar quantities. Scalar quantities, those are physical quantities but for which you only need one number. A vector quantity is a quantity that has a size, like velocity has a size, how fast you're going, and direction. You could be going east, north, west. So vector have size and direction. Scalar quantities have only size. Typically, the size or length of vectors is called magnitude, and we are going to use this word a lot, so may you get familiar with it. And we are going to represent vectors. In most cases, we're going to represent them by an arrow. Also, when we write mathematics equations, vectors are going to be represented by a letter and an arrow on top. In the book, vectors are represented by boldface characters. Let's talk about a simple vector, the displacement vector. That is a vector that goes from your starting point to your final point. In this case, this blue arrow here represents the displacement vector for Jane. Jane starts here and ends up here. That is a displacement vector. Sam, on the other hand, has this displacement vector. Sam starts here and ends up here. You see, this has a direction that points in this line. Sam has this direction. They both have different sizes, so they both have different distance that they cover. So distance is a scalar, right? Displacement, on the other hand, is a vector. Displacement is a vector, right? It has a direction, okay, and it has a size. Sometimes we are going to need to do mathematical operations on vectors, and the first one that we're going to do is addition. So we are going to take two vectors and find the resultant vector. So here we have A and B, and we want to find the vector A plus B. To do that, there are two ways. For now, we're going to study the graphical way to do that. And basically what we do is we draw A, then we take B and we drag it such that the tail of B coincides with the tip of A, and then we draw B, right? So this is B. And now the resultant vectors would be something like this. This is your vector A plus B, and this is A, and this is B. And so this is A plus B. So that's how you add vectors, and let's look at some examples here. So we have two vectors, P and Q. So what is a vector P plus Q? Take a minute to answer that. Well, now let's look at let's remember how to do this. You have P, right? P, this is your vector P, and redrawing it here, this is P. And now P, we want to write Q, so we are going to take the tail of Q and we are going to put it with the tip of A of P. So here, this is Q. And then your vector P plus Q This is q. Your vector p plus q is this vector that goes from here to here. So this is p plus q. So that will be this guy here, and that is what we do. So this is your vector resultant here. So that's what we've done. So one more example. So we are being asked how far is Anna? She walks 90 meters east and then 50 meters north. What is her displacement from the starting point? So she goes, the first thing when we solve a problem is that we prepare the problem. So we have this, we have to draw a coordinate system. So here we have east and north for our coordinate system, and we have markers for the distances. So we are told that she walks 90 meters, so which is about here, 90 meters east. And then after that, she walks about 50 meters north. She walks from the point where she was up to here. So you see, this is a natural addition of vectors. You're taking the tail of D2 and then you make it coincide with the tip of D1, and then you get your construction for vector addition. So the vector resultant, the net vector, is this guy that goes from 0 all the way here. So that is the displacement vector, and we would like to know how far she's gone from 0, right? So that means finding the length, the size of this guy here. To find the size of this guy, we're going to use Pythagoras. We realize that this is a triangle here. We know D1 and D2, so we can do Pythagoras quickly. So D net square, which is this square, is equal to this square plus this square. So that's 50 meters plus 90 meters, both square. And when we solve that, we get that she roughly is 100 meters away from 0. So this distance here is 100 meters, and this vector has a size of 100 meters.